Hey, what's up YouTube? My name is Abhishek, and in this video I want to talk about matrices and one of their most important applications in STEM. So what comes into your mind when you hear the word matrix? And yes, Keanu Reeves is the right answer because his movies totally transformed me as a person, just like Matrix transforms a vector. So with that being said, let's try to draw an arbitrary matrix and let's see what it does to a vector. Give me some numbers. Let's say 2, 3, 4, and 5. Any random matrix and any random vector, let's say x and y are my coordinates of that random vector, or a function, you can say anything, will be equal to, now by matrix multiplication I can say, this matrix, in more scientific terms I can state it as this matrix will work with this vector to give out 2x plus 3y as the transformed vector's x-coordinate and 4x plus 5y as the transformed vector's y-coordinate. So this is as simple as it gets. I have a 2 by 2 matrix for a two-dimensional coordinate space, which works with a vector x and y, vector with components x and y, to give a different vector with components 2x plus 3y and 4x plus 5y. Or in other ways, I can also write the x component times the x part of the operators, 2, 4, plus the y component times the y part of the operators, 3 and 5, will also give me the same thing. I mean, it's both are the similar and equally accepted notions. Will give me 2x plus 3y, similarly 4x plus 5y. So I have like any random matrix which works with a vector to give a different function basically. And I can also write a 3 by 3 matrix if I have x, y, and z axes. But now let's try to focus on 2 dimensions first. And now let's try to visualize how this thing will play out in a 2-dimensional coordinate space.
Okay, so I have this two-dimensional coordinate system in front of me, and I have this arbitrary vector pointing at some direction, and let's say its coordinates are 1, 2, 3, 4, comma 1, 2, 3, 4. So 4, comma 4. And now I'm going to and I also have 1, comma 0 and 1, comma 1 as my just reference axes for the original basis vectors. And now let's try to do a transformation on these coordinate systems. Well, this is the shear transformation. So watch what happens to this yellow vector as I try to transform the coordinate axis using a matrix operator. So as you can see here, well, first thing you can observe is that this vector's coordinate systems with respect to the transformed axes. Well, this vector still points at 1, 2, 3, 4, comma 1, 2, 3, and 4. So this vector still points at 4, comma 4, like before its transformation, similar to before its transformation. But what you observe is that this vector is pointing towards a different direction than this vector. That means this vector has been transformed using one specific matrix operator. Well, second thing you observe is that the coordinate systems are still equally spaced and are parallel to each other, and the origin is still intact. That means this is a linear transformation. But let's also not forget that this vector is now pointing towards 1, comma 1. So remember, my basis vector, my y basis vector was actually 0, comma 1 before. But now my y basis vector is now pointing towards 1, comma 1. So, but my x basis vector is still intact, 1, comma 0. Well, let's try to put this thing mathematically. 4, which was my original coordinate system of this vector, times the x-axis, the transformed x-coordinate. You need to remember where the basis vectors transform. So my basis vector, my x basis vector is still on 1, comma 0, plus 4, which is the y-coordinate of my previous untransformed vector, times the transformed y basis vector, which is now actually landing on 1, comma 1. And this will give me the actual coordinates, that is 8, comma 4 of the transformed vector. So I need to know where the basis vectors transform to make sure where the transformed vector will land. Well, my matrix of this the vector transformation will be 1, 1, 0, 1. So let's try to see another example. So again, I have this similar coordinate system, but now let's try to see a different vector. Now this vector is actually parallel to the x-axis. But as I do this similar shear transformation, what you observe is that this vector is not changing in magnitude and not changing in direction too. Well, not changing in direction is what more important for us right now. So what you observe is that as I do this transformation further and further, this vector does not change in direction. That means this vector is actually an eigenvector of this transformation. We will talk more about eigenvectors later, but for now I want you to remember that there are a few vectors in some transformations which do not change in direction at all as we transform the coordinate systems. And that is something which will be important for us later. So now let's try to visualize this thing more. Well, I can do numerous other transformations to this vector. For example, observe this other operator that I use on this vector to get a different transformation of these axes. Well, as you can see, with this transformation, both the basis vectors are now changed in such a way that this vector does not change its direction, but instead only changes its magnitude by scaling at a certain distance. In this example, this vector has scaled by a factor of 1.5. So, I will leave you guys this exercise to give me one possible matrix operator that can make sure that this vector does not change its direction from 1, 1, but is just scaled by a factor of 1.5. So please let me know in the comments if you have any matrix like that in mind. And now let's try to see a different vector. So now this vector is actually the vector that is parallel to the x-axis. In our last example, this vector did not change. But in this transformation, as you can see, this vector will also change its direction. So my point of saying is, different operators act on vectors to give different vectors, to spit out different types of vectors. A certain operator can transform a vector in a way, and a different operator can transform the vector in a different way. So let's try to get more into the mathematics of these operators and see what they can do in terms of its scaling and its rotation.
So now you may get it. A matrix usually acts on a vector as an operator or a function to give a different vector or a different function. So let's try to have more examples for a better understanding. Let's take one 2 by 2 matrix example or two-dimensional vector example. 1, 3, 2, 0, some random number. And let's say I have x and y coordinate. Let's also draw the coordinate systems here. Let's say I have 1, 1 as my coordinate axis. So this will be 1, 1, and this matrix will operate on this vector to give me 1 plus 3 and 2 plus 0. Simple transformation, nothing to confuse about. So 1, 1 has now become 4, 2. Something like x will be 4 and y will be 2. I hope you get what I'm trying to say here, because my drawing is not very good. So 4, 2 will be my transform matrix. But it's also important to know how the basis vector transforms, because it's not only vector that gets transformed by a matrix. In fact, all the grids of the coordinate system, each and every vector, basis vectors also get changed. So let's try to see how the basis vectors change. My x coordinate, my y coordinate, my original x and y coordinate. And now let's try to see what basis vectors do on this matrix. So my basis vectors will be this operator will decide where the basis vector will land. So 1, 2 will be my coordinates for the x-axis basis vectors, or the x-axis just 1, 2. So this will be something my x-axis, which is 1, 2. and my y basis vector will land on 3, 0. So this will be my y basis vector. So you see, having a 0 and having only an x component for the y vector will simply give me the y vector projected on a previous x vector. You will try to get this thing more clearly when you try to solve more examples. So let's try to get another example where I try to include a 3 by 3 matrix. Okay, in a 3 by 3 matrix. Now here, after 8 minutes of trying hard, I've still done horrible. This is the drawing that I came up with. So this is my x-axis, this is my y-axis, and this is my z-axis. And this is my vector 1, 2, 3. And this is my transformation matrix that I propose. And now let's see what happens to this vector when I try to operate it with this 3 by 3 matrix. 1, 2, 3 are my x, y, and z-axes. Will be equal to, now this will be my new vector, brand new vector, which will be spitted out by this matrix and this vector. 1 plus 6 plus 3, 10. This will be 3 plus 2 plus 0, 5. And this will be 1 plus 0 plus 12, which will be 30. So you see, my new x-axis is 10, new y-axis is 5, and the new z-axis is 13. Well, it will be very hard for me to draw this thing, but let's see. My x-axis will be 10, y-axis will be 5. Let's say this is 5. And my z-axis will be, oh my god, 13. So my new vector will be somewhere here, which will be 10, 5, 13. Please forgive me for the horrible drawing. But again, this is how your thought process should go when you try to use matrices with equations. Simply a matrix works with a vector to give a different vector. Let's talk something more about transformations. Let's talk about rotations. Rotations are easy. Now, for examples, if I want this vector 4, 1 to rotate exactly 90 degrees clockwise, then let's try to see what happens. There's one general formula that you should use. Now, if there's any angle by which you want to rotate a vector, simply use the x components of the transformation as cosine theta, sine theta, and the y components as negative sine theta and cosine theta. I won't go into its derivations, but these are the this is the matrix that you would use for a pure rotation. Now here, for example, I want to rotate this vector by 90 degrees. And since we are talking about clockwise rotation, theta will be negative. So as if I take theta as negative 90 degrees, what I will get here in this matrix, the cosine thetas will be 0. Negative sine theta will be equal to 1. Since sine of negative 90 is negative 1. And this will be minus 1. Now, I operate this matrix with this vector. I get 1 and I get minus 4, which actually makes sense because this vector is actually 1, negative 4, which is a rotated matrix of this vector. Similarly, in 3 dimensions. This is something that you should be using for 3 dimensions. So, 3-dimensional rotations can happen in 3 different ways. One, there is rotation that happens around y and z plane, y and z plane. The other one, where the rotation happens around x and z plane, x and z plane. And the third rotation that happens around x and y plane. So, first of all, for y and z plane, you will use this matrix 1, 0, 0, 0 cosine negative sine, and 0 sine and cosine. So for that, solving this matrix with x, y, and z, any component that you take in this matrix, you will get x component as it is, y component as y cos minus z sine, Theta will be any angle that you want to rotate this vector into. And your z component will be y sine plus z cos. So you have y and z components rotated, y cos minus z sine and y sine plus z cos by the right hand rule. So now let's try to use the other transformation or other rotation around the axes of x and z, where the y-axis is constant. So here let's try to solve for the y part first, which will just be 0 plus y plus 0. So y will stay constant as usual, but your x and z will be rotated by clockwise. Well, it all depends on your angle. So your x will be x cosine plus z sine, and your z component will be, well, I'll try to write it in a different way. Z cosine minus x sine. And now, for a different method, let's try to solve for the rotation around the xy plane. Here, your z component will be constant, and here you will get x cosine minus y sine and x sine plus y cosine. And with the help of this matrix, just plug in the value of theta that you want, and you'll get the matrix that is rotated around a certain plane with a certain angle.
In fact, when you try to include pure rotations in your transformation, you actually won't get any vector that has similar directions than its untransformed counterpart. Well, in this example, I am including pure clockwise rotation for both the axes. And check this out, all the vectors are actually not changing its magnitude, but instead they're changing its direction each and every time I do the transformation. And there is no vector in this space which has the similar direction after this transformation. More on the rotations in my next video.
I believe we have covered everything that is required to understand the basics of how matrices are used as operators to operate on certain vectors or functions to give out different functions and vectors. Maybe scaled, maybe not scaled, maybe rotated, maybe not rotated. In the next video, I will talk about the special cases where you don't get any rotated vector for a certain operator, but only get a vector that is scaled, which will be the eigenvector, and how complex numbers chip in this whole process to give out some really interesting answers. Until then, thank you very much for watching. Subscribe for more.